Hey calculus, alright, this is it, last new material for calculus. Crazy, huh? Alright, well this is average velocity and average value, and it's pretty easy, not too bad. Average velocity is just displacement over time. Now remember, displacement is another name for the original function. So for average velocity, we have to take the antiderivative, so that's why you see an integral here, an antiderivative of the velocity, v of t. An antiderivative of the velocity is the displacement, and we just simply take that displacement and we divide it by the time interval. You'll always be given a function and a time interval. You'll always be given the velocity and a time interval. Okay, so let's look at the first example here. Right here. The velocity of a moving object is given by this function. So this is our velocity right here. So we're given the velocity, v of t, right there stands for velocity. And then our time interval is from 2 to 11. So to set up our average velocity, we need the antiderivative of our velocity, 12t minus t squared dt. You need a good definite integral, and we're taking that and we're dividing it by our right endpoint, which is 11, minus our left endpoint, which is 2. So again, you need a definite integral in your numerator. All right, now a definite integral, we need our endpoints there, huh? So our our endpoints are 2 to 11. That should be in the numerator. So this is the displacement. Again, the antiderivative, that's what the big elongated S stands for, of our velocity is the displacement over time. All right, on top, I am thinking we can just use math 9. Let's go easy, math 9. So when we math 9 the top, I am getting 261. On the bottom, 11 minus 2 is 9, and then when we divide that, 261 divided by 9, I am getting 29. Now that is an average velocity. Velocity is the derivative, the rate of change. So we need units. All right, and let's see, we didn't get units here, so we're just going to say feet per second because it's a velocity. All right, so there we go. That's the first example. Okay, now what's the difference between average velocity and average value? The only difference is the kind of function you're given. If you're given a velocity function, you find average velocity. If you're just given a regular function f of x, right here I'm going to highlight it, if you're just given a function f of x, any old random function, then it's called average value. All right, and they're the same. Here we're taking the antiderivative of the function that we're given and we're dividing it by our interval, the right endpoint minus the left. Okay, so let's just clarify that. When we find average velocity, that is when we are given the velocity function. All right, and it is called average value if we are just given a function, f of x. All right? Okay, so the mean value theorem for integrals, we're going to come back to that, but we're going to go down to example number 2 now. All right? So the first thing that we need to do for example number 2 is to sketch the graph of the given function. All right? So the function that we are given in example 1, let's bring down our function. So v of t was equal to 12t minus t squared. Okay, so the first thing example 2 says is to sketch the graph of the velocity function example 1. So if I sketch that graph, it's going to be a parabola that opens down because it's a negative t squared. So grab your calculators and let's sketch a nice easy graph of this. I'm just going to scale my x-axis by, or my y-axis by tens. All right, because obviously we can't scale by ones. I'm going to scale my x-axis. I need it from 2 to 11. So here's 2, 3, 4, 5, 6, 7, 8, 9, 10, and there's 11. So there's my interval, all right, 2 to 11. The vertex of this parabola, I'm just looking at the graph, the vertex here looks to me to be 636. All right, so if we just kind of go over 6 and go up to about 36, it's about right there. All right. So it doesn't have to be anything perfect. All right, and this comes and crosses over here somewhere, and this crosses somewhere on the other side of 11. Okay, so I'm just looking at a general picture of the graph. Okay, so now we're going to go to the next part. It says use the given information from example 1. We want to find a point C in the given interval. So we want to find a point C here, some x value between 2 and 11, for which the conclusion of the mean value theorem for definite integrals is true. So the mean value theorem, here it is, mean value theorem for definite integrals, we're simply going to set our average velocity, which we already found in example number 1, equal to the velocity. All right, that's what we do. All right, so again, for the mean value theorem for integrals, we take the average velocity and we set it equal to the velocity. The average velocity we found. All right, the average velocity is right up here. We found it. For this velocity function, for this interval, this is our average velocity, so we plug that in right here. All right, and then for the velocity function, we just plug in our function. In fact, I'm going to be even more clear. This is the velocity function. All right, and our velocity function was 12t minus t squared. So that's it. Mean value theorem for integrals. So now we solve this. The easiest way to solve this is if you have a t squared and a t, is you get everything to one side and get it set equal to 0. So I'm just going to subtract 29 from both sides. So I get 0 is equal to, and I'm going to put my terms in order, so negative t squared, and then I have plus 12t, and then of course I have minus 29. All right, so the easiest way I can tell you to do that is do that, and now we quad formula. All right, so let's see what we get. You should get two answers. I'm getting 3.35, and I am getting 8.65. Okay, so now let's go over to the graph. All right, right here. I'm going to use it in black. Okay, so let's put in our points on the graph. So 3.35 is about right here. All right, and then 8.65 is about right here. And then we're going to go up to the graph. And you can kind of see as you come across, those points are both at about 29, which is what our average velocity is. Okay, so that's it in a nutshell. All right, so we're just going to highlight it here. The mean value theorem for integrals, that is where you take your average velocity and you set it equal to the velocity function. And you're just looking for values in your interval where if you go up to the function, it corresponds with the average velocity. That's it. Now we're just going to practice it. All right? Okay, let's look at the next example. We are given just a function here. So we're going to be finding average value. Remember, if you're just given a function, you find average value. If you're given a velocity, you find average velocity. So for part A, let's go ahead. Remember, for average velocity, we have on top, we have a definite integral. My endpoints are from 1 to 5. So 1 to 5. We put our function right here, x cubed minus x plus 5. And then we need dx on the end. You need good calculus notation. And then on the bottom, it's just the right endpoint 5 minus the left endpoint 1. So this is the formula for average value. The antiderivative of your function, a definite integral on top, and then the right endpoint minus the left endpoint. So let's solve this. On top, of course, you may use Math 9 to solve a definite integral. I am getting 164. Make sure you practice that. On the bottom, 5 minus 1 is 4. So 164 divided by 4 is going to look like 41. So there is our average value. All right. So let's go to part B. Part B is to sketch a graph. So let's just get a graph going here. This is a cubic curve. Our interval is from 1 out to 5. If I plug in 1 into my function, it's obviously going to be 1, 5. So we can plot that point. And so our cubic curve is going to kind of come up like this, and we only want that part. So it's just going to kind of be like this. So you don't need anything too perfect. So there's our graph for now. Let's go to part C, because that'll help us finish the graph. Part C. Okay, part C is the mean value theorem. All right, find the point in our interval that makes the conclusion of the mean value theorem work. So we're looking for a value somewhere in here. So remember, for the mean value theorem, all right, so this is the mean value theorem, and that's of course for integrals, but we take the average value and we set it equal to our function. Okay? So our average value we just found is 41. So we're going to plug that in right here. So 41, and we set that equal to our function. So that's equal to x cubed minus x plus 5. And then we just have to solve that algebraically. So again, I would get everything set equal to 0. So subtract 41 from both sides. So we have 0 is equal to x cubed minus x, and then 5 minus 41 gives us minus 36. So now we can use the calculator to find an x-intercept. Okay, so I'm seeing that cross at 3.4. Use your calculator intersection function. So now let's go up to the graph and let's put that in. 3.4 is about right here. So 3.4. And then we go up to the graph. And now obviously my graph isn't perfect, but when we go across, that right here is going to be where 41 is. Okay, so that is the mean value theorem. You set your average value, which we just found up here with this whole thing, equal to our function. We solve and get an x value. We put that x value on the graph. We go up to the graph, and if you do it correctly, you're going to come over here, and it's going to give you, it's going to be right where that average value is. All right, there we go. Okay, calculus, I think that's good enough. I think we did 2 examples where we found average value and average velocity. Setting up this whole gig right here, you have a definite integral on top, your right endpoint minus your left endpoint. You can sketch the graph, and to find the mean value theorem, you just set your average value or your average velocity, and you set it equal to your function. And then you can just add that into the graph. All right, so go ahead now and head over and do the 10-3 practice worksheet. Make sure you check your solutions online, and we will talk later, Calc. Bye-bye.